No, I didn't. Now I am. Okay, so like I said, the center of mass is the point where all of the mass, in this case m1 plus m2, is concentrated. It may not be a point in the body, but if you think of it that way, and you think of this mobile, this potato is in equilibrium, right? It's not rotating, it's not translating. I'm not trying to dance. But the point is, the net torque must be zero. So if you imagine, suppose I say, okay, is it possible that the center of mass be here? Now, if you say that the center of mass is a point in space like that, that is where all of the weight is concentrated. Now, clearly, if you look at this mobile, there is a tension force upwards, right, over here, from the string that is holding it up. Now, if you look at this, if those are the two forces acting on my potato, the tension up and the gravitational weight, which is concentrated at the center of mass, these two forces cannot be in equilibrium, right? Because if one is pulling that way, one is pulling that way, what would happen to the mobile? It will rotate. Which way would it rotate? Clockwise or counterclockwise? There you have it. It cannot be in equilibrium. The only way it can be in equilibrium is if the center of mass were somewhere along the line. This is where the center of mass is. This is where the total mass will be concentrated. Because if you now look at the tension and M1 and M2, they are lined up, they are pulling on it. What happens? Does it rotate? No, it doesn't rotate. In fact, now you know that the tension must be equal to M1 plus M2 times G. So the net vertical force is zero, and the net torque will be zero too. Therefore, it is in equilibrium. So I can tell you that the balance point, which is this point, all right, must be supported through its center of mass. More accurately, the center of mass must be somewhere below the balance point. Okay, it must be somewhere along this vertical line. Now you can apply the same consideration. I already mentioned this earlier, but when I mentioned this, you didn't know Newton's second law in rotational form, which is that net torque is I times by the angular acceleration. Now you can understand why the center of mass must be, you see, you suspend it about this point A, and the center of mass must be somewhere below this suspension point, just like the previous mobile case. All right, and it's easy to understand why. All you do is you just consider, as I wrote down here, just consider what would happen if you displace the object slightly. So if you imagine moving this object, swing it to the right. So it is hanging there, okay? And I claim that the center of mass is somewhere along the vertical line. So if you swing it to the left, right? If you swing it to the left, the center of mass is now somewhere over here. What would be the torque exerted about the point where it is suspended, about the point A? Can you see that if you bring it to the left, the torque wants to rotate it counterclockwise. So it will rotate back to the right. If you move it to the left, the torque wants to rotate it back to the left. So it would not be in equilibrium except if the center of mass is right along the vertical. And if that's the case, all you have to do is to suspend it at 2 points, and the 2 lines will have to intersect at the center of mass. That's how you can locate it. All right? Now, this concept that the center of mass must be along the line of suspension, and if you displace it slightly, there will be a torque that would want to rotate the body one way or the other, would allow you to understand something called stability. Now just look at these three figures, the three blocks. Now the three blocks are different in that their center of masses are located at different points. These are not uniform, not constant material, okay? It is different, made of different materials, and therefore their center of masses are located at different points. So if you look at number one, the center of mass is located at this point, all right, at this point. And I've drawn the vertical line. Now, if you look at the vertical line, it is right at number one, it is right at the corner, right, of this tilted box. And I claim that as long as it's in the corner, it would stay stationary. If you look at number two, the center of mass is high up there, but if you draw the vertical line down, because the center of mass is where all of the mass is concentrated, that's where the force of gravity, okay, so the weight is along the vertical white line. That's the direction of the force. Contrast that to number three. All I did was I shifted the center of mass slightly to the right. Now you notice that when you draw the vertical line, it no longer passes through the base. The base is, this point, the base of the box, right, where it is in contact with the inclined plane. Can you see that in number three, it's different? The vertical line, the line of the gravitational force, is now outside of the base of support. Now, what happens if you think about torques exerted by the weight, by this weight? Can you see that in number three, it will topple over? Because once you shift it out of the balance, the base, once it is beyond the base, if you think about the torque, right, the weight wants to rotate it this way. And the contact point is only the tip. So if anything, remember, you are pressing down on the surface, right? The normal force is upwards. So both of them want to rotate it. If you contrast it to number two, the weight, if you think about rotating it about this edge, the weight wants to rotate it counterclockwise. If there is a contact force, a normal force, the normal force wants to rotate it the other way. They can balance each other and stay in equilibrium. It will not fall over. But when it is over the edge, both the normal force and the weight want to topple it. So it will not stay over, it will just fall down. Okay? Now, this can be used to understand a lot of things. Now, as I mentioned before, my center of mass is inside my body now. Now, if I bend over, my center of mass is actually moving out. Now, what do I do when I bend over? What does your body do? What's that? What is your base of support in this case? When I'm standing up, what's the base of my support? My footprint. Okay? So you'll notice that when I bend over, I have a tendency to stick my butt in the opposite direction. Because when I bend over, I want to make sure that my center of mass is over my foot. Because if it is over, I'll topple over. Okay? So if you look at your footprint, if you bend this way, that's why you have to stick your butt out here, so that your center of mass still is within your footprint. Now you understand why sports cars have very low center of mass. Because it's not stable, right? If your center of mass is very low, you can move it. You see, if the center of mass is over here, it is beyond the base. But if you move it farther down, it can still be within the base. The lower your center of mass, the more room you have. Okay, so that you can still stay within your base. That's why when you pack up your moving truck, they always tell you put the heavy stuff at the bottom, not just so that it doesn't get squished. You don't put the heavy stuff on top to squish the lighter stuff, but also because you want to keep the center of mass low so you're more stable. Okay, this is a picture in your textbook. If you stand on the chair and you lean over to clean the window, you will kick your leg the other way, like what she did, so that your center of mass remains over your foot. Now, this toy, I think people have seen this toy before, right? Look, it's very stable. I can do a lot of things to it, and it doesn't topple over. And the reason is, if you think, I'm balancing on where the beak of the eagle is. All right, so my potato, my eagle, has whatever shape it does. I don't care what the shape is. My point is, if you think about it, if I make it such that the center of mass is over here, then in equilibrium, you know it is right down there, right along the line of support. The nice thing about this is what happens if you displace it to the right. Like I said before, the torque wants to bring it back to the left. You displace it to the left, the torque wants to bring it back to the right. It is in what we call stable equilibrium. So no matter how you move this, you see, if I move it to your right, the torque wants to bring it back to the left. The wings are weighted. You would think that the center of mass is over here. No. You have to make it such that the center of mass is beneath the balance point. That's where the center of mass is. Now you can go make whatever shape you want. As long as you make it such that the center of mass is low, below the balance point, it will come to some kind of equilibrium and it will be very stable. Now, you all know how a pregnant woman walks. They walk this way, right? Not because they want to show off their belly, but now you understand why. Why is that? What do they have to do?
Maintain balance.
To maintain balance, what do you have to do? What have we learned? What do you have to do to keep in balance? Your center of mass must be above your footprint. It cannot be over. See, as the baby grows, your center of mass grows outwards, right? So you've got to lean back to bring the center of mass back within your footprint. So for those of you who plan to get pregnant and you don't want to do this, you know what you should do? Either become an Eskimo and wear a very big shoe, or you become a hobo and carry something with weight behind so that your center of mass is always within your footprint. Backpack would work too, yes. But, I do not know if you want to do that. You carry enough weight, you don't want to add more to it. Okay. Now, as an example, this is a very quick problem. A baseball bat balances 71.1 centimeters from one end. So if you imagine you have a baseball bat, this is one end, right? And it balances 71.1 centimeters. So 71.1 centimeters, it balances at this point, right? That means if I hold a finger to it and at this point, it balances. What that means is, where is the center of mass? it must be along that vertical line. The balance point must be where the center of mass along that line, that vertical line. Okay? Here, the center of mass is directly above the vertical line, so that the net torque is still 0. If you displace it ever slightly to the right or left, what would happen to your baseball bat? It would fall. It's unstable equilibrium. Unlike the eagle, you balance, where's the center of mass? Below. So if you move it to the right, it comes back. You move it to the left, it comes back. If you're above, you move it to the right, it keeps going to the right, right? If you imagine the weight is this way, the torque is this way, it will keep going. It's not stable. But as long as it is above, it will balance. So telling you that it balances 71.1 centimeters from one end just tells you where the center of mass of the baseball bat is. All right, then they say, if you now attach a 0.56 kilogram glove to that end, okay, one end, this is the one end, 71.1 centimeters. Now you hang a glove there, which means that the weight of the glove, 0.56 G, is pulling down on that end. So to balance it, you have to move your balance point 24.7 centimeters. So you now have to move your balance point this way towards the end where you place the glove. And you move it 24.7 centimeters. All right, the question that is asked is, find the mass of the bat. Okay, you now know that when you hang the glove here, the balance point is now over here. So if you ask what forces are acting on my bat, I can draw the free body diagram. There is the 0.56 G. There is the mass of the bat times by G, acting at its center of mass. And where it is balanced, there is an upward force. You know, it presses down on your finger when you balance it. Your finger pushes back up on the bat. So those are the three forces acting. And now you can apply all the conditions for equilibrium, among which is, I do not know the force exerted. This is the normal force. I do not know the force exerted. But I don't have to know what it is if I take torque about that point. Can you see that if I take torque about this point, the normal force exerts 0 torque? Now, what about this force, the weight of the bat? Is it a positive or negative torque? Is it clockwise or counterclockwise? Clockwise, right? The torque due to the weight mg is clockwise, therefore it's negative. So you say it's minus mg times by 0.247. Now, the baseball glove has a counterclockwise torque, so it's positive, and the torque would be the force, 0.56 G, times by the moment on the perpendicular distance, which would be this distance, which is 71.1 minus 24.7. 46.4. So I've got to convert that to 0.466 centimeters. This must sum to 0. Now the only unknown here is m. You can just use this and figure out what m is, and it works out to be 1.05 kilograms. Okay, let's try your hand on this pole. What's that?
You can't see the work on the back, huh?
You should be able to do it on your own. I keep telling you, try and go back and do it on your own, because that's the only way you would learn. All right, this one you have, this ruler is balanced at this point. And you balance it at that point when you hang a 1 kilogram object on one end of this rod. The question is, if the rod is uniform, that's what we assume, and it balances at a point 0.25 meters away from this 1 meter from one end of this 1 meter rod, what is the mass of the rod? That's the question. Okay, I'm going to start the poll now and see if you can answer it. So that's the picture. This is 0.25 meters, and this is 1 meter. Okay, let's move it down to here and see what you get. Now, this is a uniform rod. So where is the center of mass of the uniform rod? Half a meter, at the half meter mark, at the center, at the geometric center of the ruler, of the rod. In other words, here. So this is an unknown mass, m, and that's the weight. This thing is in equilibrium. What is that unknown mass? The rod M. This is a 5-second question. So in the exam, I multiply by 10. 1 minute, you should be done. Yes, is it done? Is everyone done? I'm going to shut it down soon. Understand what the difficulty is. Is everyone done? Not done? Oh, I can help you. Mg times by what? Mg is mass times gravity. You multiply by what? What is that distance? Center of mass to where? When you take torque, you have to take torque about a certain point, right? What point are you going to take it about? No, I'm talking about taking torque. About, you know, the condition for equilibrium is the net torque must be 0. But net torque about what point? Then you have to ask yourself what that distance is. Yes. You always have to take an axis of rotation. And You have to know how to take torque. You don't learn that, you'll not be able to take torque about anything. So you take torque about the balance point, that is your axis of rotation. Sometimes I feel like killing myself. But I take pills. I'm naturally high on life, don't worry. So you take torque about this point, you have to know how to take torque about a point, an axis of rotation. That's where your mistake is. If you take torque about this point, remember there are three forces acting. There's another force upwards. And if you take torque about this point, you don't care about what that force is. So everything that you do, you have to understand why you pick this point. I mean, I told you, if you go back and you do it, you would understand it. All the amount of me telling you doesn't tell you anything. But if you take torque about this point, it is still going to be 0. And then this unknown force will come into play. In fact, I can ask you, what is that unknown force? What is that unknown force? 1 plus m. It's just some Fy equal to 0. This is a body in equilibrium. There are only three things. Sum of all x component of forces equals 0. Sum of y component of all forces 0. Sum of torque about any one point equals 0. I can tell you now there will be a question like that on the exam. And if you don't want to go back and learn how to do it, you only have yourself to blame. Okay, let me go on to the next topic. Now, this is even more difficult. If you have trouble with applications of Newton's law, this one just adds more to it. And that is, you now have, as an example, a pulley, a flywheel, whatever you have, something that is going to be able to rotate. You attach a rope around it, and you hang a weight on the other end. Now, when you let it go, you know from experience this mass is going to drop. It's going to accelerate. The question is, if this pulley here, if that has mass and therefore it's got moments of inertia, if it can rotate, would it affect the motion? And the obvious answer is yes. If you want to look at it from the energy point of view, you would know that as this object falls, it loses. What does it lose when it falls? What's that? Potential energy. So what happens to the loss in potential energy? It becomes kinetic energy. Kinetic energy of what? You have the kinetic energy of this falling mass, but because you have a pulley, you have a disc, it can rotate, therefore it too will have kinetic energy. It will have rotational kinetic energy. Therefore, you can see very quickly from the energy point of view, the fact that it has mass and can rotate thus affects the motion. Now, the question is, how do you solve for something like this? The answer always is, you draw free body diagrams. Then you apply Newton's second law. Then you solve. It's just that now part of your motion is not just translation, it has rotation too. And in this example, you've got two bodies, so you draw two free body diagrams. The first one is the falling mass. Very simple. You have the tension up, you've got the weight down. And if it is accelerating downwards, what would Newton's second law give you? I don't like that this is positive. I'm going to call this positive. Then mg minus t is m times a, because a is downwards. So I'll call downwards positive. That's just Newton's second law. Now there is something different. You have another body. It too is capable of motion. Here the motion is rotation, that's all. So you draw the free body diagram. That's this one. And now you notice that it has a force exerted on it, and it is rotating. So you have to apply Newton's second law, which is that the torque is the force times by the moment arm. Now it is rotating about the center, right? About this center here. So this is the line of force. This is the perpendicular distance. That's the moment arm. That's just r. The big R in this case, the radius of the disk. So torque must be equal to moment of inertia I times by alpha. Okay, that is an equation of motion for the rotational system. Now, the thing about this problem is that this is all worked out in your book. If the rope doesn't slip, there is a simple relation between A and alpha. A is equal to R alpha. Now, if you are given that this is a disk, I is 1/2 mass, I'll use the notation in the diagram, mass of the disk, the pulley, 1/2 m radius of the pulley squared. So with all these relations, you can now solve for the tension and the acceleration. Now, you can go back and look at another example that is done in the book. That one is more complicated than this. That problem looks like this. You have a pulley, you have a mass, you have another hanging mass. So this is your table. Now that you have a pulley, it can rotate. Now it gets complicated now, so I'll just mention it to you. If the pulley were smooth, what happens? If the pulley were perfect, if the surface of the pulley were perfectly smooth, and you have a rope over it, what would happen to the rope as the object falls? It will just slide over. That means the pulley doesn't experience any force. There is no roughness, no friction to cause the pulley to rotate. Then this problem becomes exactly like the problem that you did before. Or if you want, I say that the pulley is massless. If the pulley is massless, it can rotate all at once. Its I is 0. So the torque must be 0, right? Newton's second law, sum tau equal I alpha. If I is 0, the net torque must be 0. So in all the previous problems that you did, you say, oh, there is a tension in this rope, and you write them as two identical tensions. It's because either you consider the pulley to be perfectly smooth, or you consider it to be massless. Here, we are going to say, it now has friction, it now has mass. The consequence of that is the tensions are now no longer the same. I'll have to draw it like that, because now when I draw the free body diagram for the pulley, there is a T2 here, there's a T1 here, and for rotation about this, T2 is a clockwise torque, T1 is a counterclockwise torque. So now there is a net non-zero torque acting. And then you apply Newton's second law. Net torque is I alpha. If you know the moment of inertia of that, you have alpha. If there's no slipping, alpha and the acceleration of this and the acceleration of that are related in the same usual manner. So it just complicates your life tremendously. All right. But in principle, it's just algebra. In principle, if you think about it in a logical manner, you know all the physics behind it. You can just do it. Let me go on to some examples. I only do the simple examples where there isn't as much, there is only fixed rope. So there's only one tension. In other words, I have ropes that are tied around a turning object, just like the previous example, the one where we just drew. If there's only one rope that is tied around, it doesn't sling over to the other side and have a different mass here, then the two sides will have two different tensions. But here, like that, you only have one tension here, like that. So same kind of problem here. You have problem number 46 and 47 are together. It says you have a 2.85 kilogram bucket and attached to a disc-shaped pulley. So once again, I do not know why they like disc-shaped pulley. And you have a bucket that attached to it. This is 2.85 kilograms. So that's the force of gravity there. The pulley has a radius of 0.121 meters and a mass 0.742 kilograms. All right. Now the bucket is allowed to fall. What is its linear acceleration? What is its angular acceleration of the pulley? How far does the bucket drop in 1.5 seconds? What is the tension in the rope? Can ask you a bunch of questions related to this. This is identical to the problem that I started out with, right? You draw a free body diagram for the bucket. You have tension. You have the weight, and it is accelerating downwards, A. That's the linear acceleration it's asking for. Now you draw the free body diagram for the pulley. Yeah, the pulley. Then you find that you have the same rope, so it's the same tension. This thing would now rotate. It has an angular acceleration alpha. Okay? And you apply Newton's second law, you say net torque, since there's only one rope pulling down, there's only one tension, you say that the torque is the tension multiplied by the radius, which is 0.121. This must be equal to I, which is the moment of inertia of the disk. This is 1/2 mass, 0.742 R, 0.121 squared. This is just I. Okay? And Newton's second law is torque equals I alpha. Now, this thing is rotating, and this thing is falling down, translating. And the tangential acceleration is the acceleration of the bucket. So in other words, A is equal to R alpha. Okay? Now, over here, I put in the numbers. Sometimes you don't have to one of the radius cancels, and 0.121 alpha is A, and it turns out this is 1/2 0.742 A. The tension is equal to that. And now you come to this, you will have Newton's second law, 2.85 G minus the tension is equal to 2.85 A. Okay?
Wait, that's an alpha, right? Not the sign A?
No, that's A. That's R alpha. R alpha is A. So you have two equations now. You can substitute for T into here. You can solve for A. So that's the first part. What is the linear acceleration? If you want to know what the angular acceleration is, you know A, you can find out alpha. That's the angular acceleration. Now, how far does the bucket drop in 1.5 seconds? How would you answer that question? It's just kinematics. You have acceleration, you have time, you have initial velocity. You assume the bucket starts from rest, right? And they are asking for how far a distance, if you want, x minus x naught. Or if you want to call the initial position 0, that means x0 equals 0. Then all you're calculating for is x. So that is just something from chapter 2. And finally, what is the tension in the rope? If I know, from here and here, if I can calculate A, then I know the tension in the rope. Okay? So you see, it only makes the problem more involved. It doesn't make it more difficult. It's really not that difficult. You just have to go through each step. The only thing, like I said, is instead of it translating, it is rotating. And then you always have to have tangential acceleration, which is the acceleration of the falling object. See, I can make your life much more difficult if I tell you there's something like this, M1 and M2. Then you have two different tensions. And you've got 3 bodies that you've got to write down, right? Free body diagram for this, free body diagram for this, free body diagram for that. But in principle, it's not more complicated. I do not know. It's not more difficult. You just have one more diagram, one more equation, one more unknown, one more thing to solve. Here, in this problem, there are 2 unknowns, right? The acceleration and the tension. Here, you've got 3 unknowns. Acceleration, tension 1, tension 2. I can make your life hell if I put a spring over here and then have a third mass. That one you can't solve. You can't solve that problem without calculus. Okay, as another example, 48 is this. A child exerts a tangential force on the rim of a disc-shaped merry-go-round with a radius. If the merry-go-round starts at rest and acquires an angular speed of 0.086 revolutions per second in 3.5 seconds, what is its mass? Now, this problem, don't worry, don't have nightmares. I'm not going to make you do that problem. All right, this one looks like this. You have a merry-go-round that looks like a disc, and you apply a tangential force. So tangential means this. All right? Now, the radius is given to you 2.40 meters. And the merry-go-round starts at rest. That means omega 0 is 0. Your final is 0.086 revolutions per second. And the time is 3.50 seconds later. They want to know what is the mass. All right. Now, in this case, what you do is you say, okay, I'm given omega naught t, and I want to find m. If you don't know where to go from here, just don't worry. You just start writing down things. One thing you know is this is motion. Motion means Newton's second law. Newton's second law for rotational form is torque equals I alpha. Then you look at this system, you say, what is the torque? There's only one external force. What is the torque? Force times by the perpendicular distance, the moment arm, right, which would be 2.40. And that's because they are 90 degrees. If you want to use RF sine theta, it's 2.4 times 42.2 times by sine of 90 degrees. Same thing. Whatever poison you pick. Okay, so that's the net torque. This must be equal to I for the disk now. We know this is 1/2 m. That's the unknown. Times by r squared. So this is I times by alpha. So you say, in this equation, I have two unknowns. What do I want to find? M. Say, okay, this equation is potentially useful. But in order for me to find M, I have to work out alpha. Okay. Then to work out alpha, you have to see what else is given to you. And then you've got to recognize, okay, this thing has a constant torque, it's got a constant angular acceleration. Therefore, I can use the kinematic equations, which is that omega is omega naught plus alpha t. Then I have omega. Now, in order to do this, I really have to change revolutions per second to radians per second, okay? The unit that you have to use will be the pure units, the radians. So if one revolution is 2 pi, what is a quarter of a revolution? What is half a revolution? What is 0.086 of a revolution? How many radians is that? Right? If it is 1 revolution, it's just 2 pi radians. Whatever fraction of it, that's the number of amount of radians that you rotate. So that's omega naught alpha 3.5. Oh, I'm done. I know alpha. I can jump with joy now because once I know alpha, I know m. All right. Now you can say, how do I know to use this? My answer to you is, well, it's through experience. I have all those formulas imprinted in my head. I sift through them. I know exactly which one to use. If you don't know, what do? You look at every equation in there, and then one of them would work. Now, that also presumes that you recognize this is kinematics, and you know where in your cheat sheet. By the way, if you kept your cheat sheet from exam 1 and 2, you can use them. If not, you've got to redo them again. Then you can add a third cheat sheet if you want.
We can have 3 papers for the exam.
What's that?
We can have 3 papers for the exam.
Right. It doesn't really help you, I tell you. I just want you to be pacified, that's all, that you're not nervous. But really, I keep telling people it doesn't help you unless you know what to look for. If you just think, oh, I can bring in cheat sheet, I put everything down, I don't have to study, I don't have to do homework, I just copy answers down, you're not going to do well in the exam. And this will repeat itself in 100B when you do take it. So you have got to learn how to work properly. Yeah.
For this equation, couldn't we also find alpha by making it equal to the change in angular speed over given time?
Alpha equals omega minus omega naught over time. That's exactly this equation, right? We got this equation from this. Yeah. So this is from definition. When your acceleration is constant, then it's just change in velocity over time. It's equal to the average acceleration, in other words. Okay. All right. There's still a lot in this chapter, but they're all the same. This one I want to do because it's very interesting. The last section is even more interesting, but I can't even get there. Someone here must have said, no, I hope not. I hope no one had looked down the barrel of a rifle before. But if you do, you'll notice that they actually put, has anyone looked down the barrel of a rifle before?
Yeah.
What do you see?
Just rifling.
Yeah, they call it rifling. They actually put spiral along the surface, and the thing is, it is put in there so that they cause the bullet, when the bullet is fired out, it will cause the bullet to do this, to spin. You know what a tight spiral is? That's a very tight spiral. That's what a good quarterback does, except that it's not throwing a bullet but a football. Do you know why they throw a tight spiral?
So instead the spider wants to hit specifically?
It won't wobble. It's for stability. It's for stability because a rotating body has what we call angular momentum. We will be talking about what that is. We'll be talking about conservation of angular momentum. And when you throw the football so it rotates, it's got angular momentum. And it turns out, just like when we studied linear momentum, if the net external force is equal to 0, linear momentum is conserved. So for a rotating body, if the net angular momentum is 0, angular momentum is conserved. And that's what it means. Conserve means it stays constant, right? So the spiraling ball that does this, the direction of the angular momentum is in the direction as you rotate. Your thumb points in that direction of the angular momentum. So it's got an angular momentum, and it wants to be constant. In a football, it is not constant because you have a net external torque, a weight. So it will rotate, but it will still want to maintain stability because in order for it to rotate the angular momentum, you need torque in a different direction. That's why the quarterback does that. So the ball does this as opposed to tumbling along. When it's a sitting duck like that, not only is it difficult to catch, but it doesn't go as far. For it to go far, for it to keep on the tight trajectory like that, you want to put spin to it. Now, how many of you here ride on a motorcycle? No one? I don't either. But you know that if you ride on the bicycle or motorcycle, you find that it's very easy to maintain balance, right? You can let go of the handle and your thing keeps going. That's because the wheels of your motorcycle and your bicycle are rotating. When they're rotating, they've got angular momentum. And the angular momentum, they want to change it, you've got to apply a torque. And in fact, you can understand now why, if you're rotating and you want to turn left, you don't have to turn the handle. What do? You lean that way. You lean that way. If you want to understand it, it's because when you lean that way, there's a net torque exerted, and the net torque leads to a change in angular momentum. So your angular momentum wants to change this way, and therefore your bike goes that way. It is stable too on a straight road. If you don't apply any external torque, the angular momentum wants to keep that way. You won't fall over. In fact, the faster you go, the more stable you are. Try to balance on the wheel when it is not rotating, and you find that it's very difficult. Because every little bit of leaning that you do, the torque will drop it over. I forgot to bring my favorite demonstration. Maybe I'll do that next time. But angular momentum has some very, very interesting properties. I'll demonstrate that at the bicycle wheel next time. If you have never seen it before, it's very interesting. So what is this angular momentum? It's more difficult to motivate, but you remember we introduced linear momentum. We say P is equal to what? What's that? mv, right? Mass times velocity. So if I say angular momentum, that's the angular analog of momentum. So instead of m, mass, what do you have? Moment of inertia. Instead of v, velocity, what would you have? Angular velocity. So we're going to define angular momentum as I omega. Okay? Now, you can do this very quickly for a single point object. It's just algebra. Right? You're going around a circle and you have a velocity v. All right, now if I ask you, what is its angular velocity? You say, it's I omega by definition. But for a single point rotating in the circle, what is I? Do you remember? It's just mr squared. All right, if all the mass were concentrated there, I don't know, this may frighten some people, but that's how you define the angular, the moment of inertia. So if you only have one object, then it's just m, and then the distance is just r squared. So mr squared omega. What is r times omega equal to? That's the tangential velocity. That's the velocity of the object. And mv is p. So you find that for at least for this point object, you can also write L as rp. Now this is only true for an object going around in a circle. This one, L equal to I omega, is true for all potatoes. It doesn't have to be a single point. I can have any shaped object rotating about some axis. The angular momentum it has would be the moment of inertia about that axis times by its angular velocity. Okay, so where does this lead us? This leads us to something more general. Remember that we are talking about angular velocity. If you're looking at a point object like this, it's moving in some direction. Okay, and if I draw a circle centered somewhere else, passing through that point, that object in general, for a given circle in general, it will not be tangential. Obviously I can, right? I can always draw it tangential. You just tell me, oh, this is the direction and this is the point, then I can draw my circle. Oops, I can pick a point there so that it is tangential. But if I pick another point, any other point, it is no longer tangential. There's only one point, if you want 2 points on the other side, where it's tangential. So in general, the angular momentum has to be modified. The more general expression looks like this. Remember that this is a vector. Velocity is a vector. Linear momentum is a vector. As with any vector, it can be broken up into its components. So in particular, I'm going to pick one that is along the radius and tangential to the radius, to the circle. So this doesn't produce any rotation, right? The angular motion is the tangential part. So if this is the angle theta, I only want the vertical component. The vertical component is sine. And we can end up with the moment arm times by p again. Instead of rp, it's r perpendicular times p. So once again, you've got a line, in this case a linear momentum, and an axis of rotation, that is a moment arm. This is quite common in some ways. I don't even know why I'm doing this, because it is only useful in solving problems. Because there's so many problems with angular momentum. One of the things is, if you have when you go to the playground, you've got a merry-go-round, and suppose it's rotating, right? I can take a running start and jump onto the merry-go-round. The question is, what happens after you jump onto the merry-go-round? To answer that question seems at first it's very complicated. Say, my God, look at this! I jump onto it. I exert a force on the merry-go-round. There's friction. I slide. I do this. I do that. How do I solve this problem? And it turns out that there are some very, very general principles that you can apply, much like we did in the case of a collection of objects. And we say the net external force is equal to rate of change of total linear momentum. We can do the same thing here. It will be the net external torque is equal to the change in angular momentum. These are just calculated angular momentum. So this is the topic that I'm talking about. When we say L is I omega, I can now ask, what is delta L? Well, if my body doesn't change shape, I would be the same. I have delta omega. So if I divide by both sides, delta omega by delta t is actually the angular acceleration, I alpha. What is I alpha? Newton's second law is the torque. And it turns out that we can write Newton's second law in terms of the angular momentum. Just like we could write Newton's second law, net external force equal delta P by delta T, the linear momentum part. That's why I say this chapter and the previous is all of the previous chapters together into rotational motion. So it covers so much material. The reason we come to this is now we get the same thing. What happens if the net external torque is zero? If the net external torque, that is this quantity, if it is equal to zero, then delta L equals zero. That means L doesn't change. That's what we mean by conservation. So we get to the situation where we say, if the net external force is zero, total linear momentum is conserved. Now we can say, if the net external torque is zero, total angular momentum is conserved. So in the case of the rotating merry-go-round, I can run onto it and jump and slide and do whatever I want to it. if my system is me and the merry-go-round, whatever force I exert on the merry-go-round exerts on me. Those are all internal forces. In other words, my act of jumping does not provide any external torque. So the key to solving that problem is angular momentum is conserved. But to calculate angular momentum, you have to know these formulas. That's what makes it difficult. So don't worry about it. I just want to talk about it. I like to listen to my voice. The reason I introduce angular momentum and conservation is how many of you, and I used to drag this thing, but we're so far from the office, from the department. You know about figure skaters, right? What do they do when they go and then they jump and then what do they do to themselves to make themselves spin very, very fast? They pull their arms in. Next time, just watch. They'll spread themselves out, and then when they land, they'll just pull everything down, and then they spin very, very fast. And what do they do to slow themselves down? They push their arms out, they push their legs out, okay? Now, that phenomenon is explained through conservation of angular momentum. When you're like that, your masses are far away from the axis, so you have large moments of inertia. That's your initial moment of inertia. Your angular momentum is I omega. So initially you've got large you have large moments of inertia. You have an angular velocity, right? You're doing this. Now if you're doing this and there is no external torque acting on you, your total angular momentum is conserved. So you're spinning slowly. If I pull my arms in, my angular momentum is conserved, right? So I initial, omega initial is a constant. Constant meaning this quantity is the same no matter when you consider. At a later stage, you have a different shape, you've got a different I, you have a different angular velocity. So if this is large, and let's say this is 10, this is 1, okay? If this is 10, that is 1, and you bring yourself in, you make your moments of inertia, instead of being 10, let's say it is 5. What happens to this? It increases, it becomes 2. So that now you understand what they are doing when they bring their arms in, change their moments of inertia. Now you understand why they speed up. They speed up because of conservation of angular momentum. Okay, there are all kinds of, this is the problem. I could have brought this in. I show this to kids that visit CSUN a lot, and they always have a lot of fun with it. Has anyone seen this or done this? If you put me on that, I'll puke. I suffer from motion sickness very easily. But you can see, you put the weight out there, when you pull your arms in, they speed up, and then when they pull it back out, they slow back down. Even with a lot of friction, it still is somewhat true. And if you experience it, you can really feel the speeding up when you bring your arms back in. Yeah, this only makes sense to those who have turntables. How many of you here have turntables? Oh, they're making a comeback. Now they're seen as expensive items. But this is, again, a collision. Whatever the racket on top, when it falls down onto the table, it will slide and slip and whatnot. But those are all internal forces, internal torques. Net angular momentum is conserved, and you use this to solve problems. Now a diver is the same thing. You know, when they dive off, they have some rotational. If you look at the diver now, you'll see that they have a certain rotational speed. They tuck their body in, they speed up, and then before they enter water, they open up again. When you open up, you spread your masses far away, you have large moment of inertia, your rotational speed decreases. So those are all examples of that. Anyway, I will show you the bicycle wheel next time, but I will have to go on to chapter 13. Okay, before you go, I have to do this. I know I'm running out of time. That's because I love my voice too much. Can someone help me and take this back to the department office? Yes. All right. Can you distribute them out? Can you just pass them back?
Before we go, can I ask a quick question? On the day of our final, December 15, I also have a bio